We've invented self-encrypting data so you can use the world's spare storage as one giant hard drive. It's how you can use space on someone else's computer and be sure no one's peeking. So I'm going to explain how self-encryption works, and I'm going to do so through the medium of Lego. So take this Lego kit. You can think of it as some of your information, your content, your file, something you want to store on the network. Now, if you want to make it secure, if you want to make it inaccessible to anyone else but you, the first thing you need to do is smash it up. So far, so good. So actually, when we're self-encrypting data for this network, all of the chunks are in a more uniform size. So they look a bit more like this. And this is the first part of self-encryption. Any file is broken into tiny chunks. This is already getting a bit tricky for anyone else to understand what's going on here, especially if you imagine it against the background noise of all the other data on the network. But we're going to take it way farther. We're going to encrypt this data with a hash of itself. Now, quick sidebar here, folks. What do I mean by encrypting with a hash of itself? Think of it like this. Imagine if you could take a Lego piece. You get it, but it's a little Lego hand on the table, and you scan its fingerprint, and then you use that fingerprint as a combination to a safe, and then you lock the Lego piece inside that safe. Here's what makes it unbreakable. To open that safe, you need the code, but the code for that safe comes from the thing that's locked inside. It's beautifully circular. The data essentially locks itself up with a key made from itself. Self-encryption. In technical terms, we call a fingerprint a hash, a unique code generated from the data that you can't reverse engineer. The only way to know that code is to know exactly what the data is. We use that code as the encryption key. Back to the Lego fun. So what's happening under the hood? We're taking this collection of chunks and making it into a loop. So each chunk gets encrypted with the hash of an adjacent chunk, one after the other. Not only is this the first process in making some unbreakable protection for your data, it's also designed to bring some really interesting qualities to the data on the network, like giving every piece of data and every chunk its own unique address. I'll dig into that in another video, but it means your data has some really useful, powerful new properties. But it's these chunks, these mystery chunks, that get scattered right across the globe, across all of these millions and billions of nodes. And what's more, each chunk gets duplicated 5 or more times. And then all these chunks get mixed up again and spread out across all of these nodes. And this makes things even more secure because there are always copies of each chunk. And these chunks are constantly moving around the network, backing up again, moving between nodes, and nodes are checking each other's homework to make sure everything is as it should be. And of course, all of these chunks are mixed up with all this other unintelligible, highly encrypted data that all looks the same, as all the same size, and it's constantly moving. And somewhere in there are the chunks that belong to me. And the only person that can look at them and unlock them is me, because I'm the one with the key. So how do I get my file back? For that, I need a map. I need a data map. And I'm the only person who has this data map. And I'm also the only person with the keys to decrypt these chunks and reassemble the file on my own device. And this special map, I can encrypt that as well. And I can store this on the network too. So this is self-encryption, your data protecting itself, making it possible to use the world's spare computing capacity as one giant hard drive without having to trust anyone but yourself.